Hello, and welcome back to Making a Programming Language, because why not? What kind of programming language are we making? So if you saw the last part, you saw that this is the kind of programming language we're trying to make. So like a stack-based programming language like Forth or, Porth, if you know Porth. Uh, and so what that means is rather than having expressions with infix binary operations like 1 plus 2 and stuff like that. Instead, it's all stack based. So as the interpreter goes through this program, it looks at each operation, and each operation will modify a stack of values. So 4, 5 plus print pushes 4 onto the stack, pushes 5 onto the stack, plus then pops off two integers, adds them together and pushes the result onto the stack, and then print pops that off the stack and prints it. So this line would print 9, and then same for this. You push 6, you push 2, pop those off, you do 2 minus 6, you print, you get minus 4, etc., etc. So since last time, I've made it so that you can just pass a path to the program. So if I pass arithmetic do, you can see it prints 9 minus 4, 20, which is 4 times 5, 4, which is 8 divided by 2, and 2, which is 5 mod 3. And then this one is showing you how you can have multiple binary expressions in this sort of language. Pushes 2, pushes 3, pushes 4, plus then pops off 4 and 3, adds them together to 7, and then so the stack is now 2, 7. Then the star is multiply, so it pops the 7, pops the 2, multiplies them together, pushes 14, as you can see, it prints 14. And the other thing you can do is you can modify the stack with special keywords like swap and dupe. So swap, as the name implies, it swaps the top two elements of a stack. So 1, 2, swap. So you have 1, 2, swap, swaps them. So you have 2, 1, and then it prints it. So you have 1, 2. And dupe just duplicates what's on the stack. So we have 5, duplicates it, duplicates it, so 5, 5, multiply, 25, prints 25. So we can have a look at that one. So yeah, 1, 2, swap. So 1 is on top, 2 is on bottom, so it prints 1, 2, and then it prints 25. So as it is, this is very similar to Forth and Porth and other like imperative style concatenative, stack-based concatenative programming languages. But with do, I want to go one further and have a more functional style of programming language. And I know, again, stuff like this exists, but this is like for my own enjoyment and to just kind of like learn and see what it is. So when I have an idea for what I want to program, I'm tempted not to look it up because I don't want to get disheartened seeing my idea already exist, because it inevitably will. I'm not very unique. It's incredibly hard to come up with an idea to program something and it be completely unique. And then the other thing is, like, I just don't want to have any ideas like put in my head on how to implement it. Like, I want to figure out how to implement it as I go. So I know that there's a language called, I think it's Factor, or there's another one called Joy. And these, I think, are like functional stack-based programming languages. I've seen snippets of the syntax, and my syntax is similar, or my planned syntax. Like, this is all the syntax we have at the moment. But we're just going to see like where this takes us, and who knows? Maybe it'll end up the exact same. Maybe it'll be worse. Doesn't matter. I had fun making it, and I'm probably learned something doing it. So if we have like lists do, what is a list like in do? So I think last time I had this sort of syntax, and so what this would do, rather than pushing like 1, 2, 3, 4, 5 onto the stack as like 5 separate values, it just pushes a single value onto the stack, which is the list. Because this is interpreted, that makes it a lot easier, because trying to compile that would be not impossible, like by any means, but it would just be more work than I want to do right now. And so I was toying with the idea of like, well, do you even need the commas? Because now you have a list of 5 operations. And I was thinking this could be the syntax for it, but that implies that you can only have push operations inside a list, which maybe we want to allow, maybe we don't, because you could conceivably have something like 1, 2, 3, 4 plus 4, 5. And so this would be the list 1, 2, 7, 4, 5, because this would evaluate to a single value. But then it becomes really tricky to find where the elements are. So I think for now, we should just have it like this, where you're only allowed push operations inside a list. So push int, and then we'll have like push bool, or push string, push float, stuff like that. So that's what lists would look like. And then you can have functions. So functions in round brackets are like you push a function, like a lambda, onto the stack. So it doesn't get executed if you do it like this. If you don't have the round brackets, you're just operating on the stack. So what this would do is it would duplicate the list, and then it would do multiply on 2 lists, which, maybe that would be handy to do something like cross product or something like that. But as is, that would probably fail. It would fail anyway because we don't have lists. But so by putting it inside the round brackets, you're saying just push this function to the stack, but don't execute it yet. And then with that, you can then push a function like map. And what that will do is it will pop off a function, and it will pop off a list, and it will apply the function to every element in the list. So this will square the entire list, and then you can do something like this, where you push the function print onto the stack, and then you call for each, which pops off a function and a list, and it applies the function to the list, to every element in the list. So that will print off all the square numbers. And the difference between these two is the signature of the function that they accept. So map accepts a function of some generic value to some other generic value. So in this case, dupe star accepts, is a function of integer to integer. But you could have something like 3 greater. And so that is a function of integer to Boolean, because this takes in every element from the list, or it will take in an integer from the list, compare it to 3. If it's greater than 3, it'll return true. Otherwise, it will return false. And so this would print like false, 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 true, true. And then for each, the signature for each is it wants a function that consumes any value and doesn't return anything. So print consumes a value, prints it, doesn't put anything onto the stack. And you can have other sort of signature, or like other function or higher order functions that accept other types of functions. So you could have, let's see, something like plus 0 reduce, and this would have to be an integer again. So if we do this, so that would square everything in this, and reduce, as you can see, I haven't added it to the syntax highlighter yet, but maybe it wouldn't be reduce, maybe it would be fold, because you kind of have to know which side you're folding, left or right, but don't worry about it. This takes in some accumulator, a function that takes in 2 values that are the same type as the accumulator, or at least a function that takes in, yeah, it has to be the same as the accumulator. So a function that takes two integers, because we have an integer here, and a list of that type, so a list of integers, and that basically just applies this function between the accumulator and every element of the list and returns a single value. So this would sum the whole list. And then afterwards you could print, and that would sum up the square numbers from 1 to 5 and print them. But none of this works yet. None of this works because we don't have lists, we don't have functions, and our type checker is a mess. So I have a little to do, and so actually I've another thing I've done is I've put this up on GitHub. So sorry for the flashbang. I've switched to dark mode now because I watched back the first episode, and though I program in light mode when I'm just programming by myself, but for a YouTube video it was a bit bright, so I've switched to dark mode. But we're going to get flashbang now. So I've put it up on GitHub, so I'll put this in the description, and it has a very simple to do. I need to write more about it, but I couldn't be bothered just yet. So you can come check it out, see what the source code looks like at the time in which you're viewing this, because if you're watching this much later than when it came out, this project might be finished, which, I don't know, unlikely. When is a language ever finished? Yeah, so I have this to do. So first of all, I want to have diagnostics, because so if we try to compile this now, first of all, I don't know if our Lexa is, well, our whole compiler is like good enough that it's going to correctly error on this, but we can give it a go. So what happens if we try and compile lists.do? Yeah, we hang. So yeah, it's not great. But if I was to go back to arithmetic.do, I just had this one. So prints 9. If I only had a single integer on the stack, plus doesn't work because there's nothing for it to pop off. So if we try and run this, okay, that's pretty good. We have expected int, but stack was empty. And there's two things wrong with this. No, there's a couple things wrong with this. But first of all, it points us to the compiler source code, which is handy if I'm the person writing the compiler. If I'm just using do, that's not very helpful. Because this is a very simple program. But imagine if this was like hundreds of lines long. Where did you expect int? I don't know. So you need to be able to report the location of the operation that failed. And it would be really nice if it would print it in a very pretty way. Like if I intentionally break my Rust code. Let's see. If I take this as a reference, which it doesn't expect, and then I try to build, you see, you get this really nice diagnostic. So first of all, it points you exactly at the location in your source code. So if you click this, it takes you to the exact token in your source code, or the exact location in your source code where the error is. It prints out the line of that source code and the line number and all this stuff, and it underlines where the error was. So if you didn't have this IDE and you were just like in a text file or in like Emacs or Vim or something, you don't have this underline. Like you can click this and it will like point you to your location in your source code. But seeing this is really nice. And like Rust is very extra. I don't know if we're going to get this point, but it will actually show you like how to fix the error, which is really nice. I don't know if we can get quite that fancy, but this is something we should be able to do, because what I did at the beginning with the Lexa is every token has a span, and this span has the offset that the token begins and how long it is. So if we go back to that broken example, this token of the ampersand, the Rust will have the location in its, compilation, and when it sees, oh, there's an error here in the type checker, it can go and get that location, and it actually it has a span of the whole expression, which we can also do, and it can then locate the point in the source code from that offset and the length of it and print that out. So we also, in our parser, so we have operations, and currently operations are one token to one operation. So though we have a span in our operation, it's basically the same as the token, but for something like lists, like this is actually 7 tokens. It's open square bracket and then the 5 integers and then close square bracket. So the span of this would be the whole array, or the whole list. So that's why we've done that. Oh, you can see my cat. So it would be really nice to have diagnostics. So I think we're going to start a new file and start making some diagnostics. Okay, so I have coffee. Let's begin. So first thing we'll probably want to do is declare the module. Let's put it above. Cool. And so what does a diagnostic look like? So I'm thinking just simply it is a message, which is a string, and it is a span of where the diagnostic is reporting. And then we also need to give it a name, because otherwise it does not make sense. So this should probably be public, and these should be public. So when you report a diagnostic, so let's have fun report, and this will return a diagnostic. So I guess really it's just a constructor. So it'll have a message, string, and a span, and then we just say diagnostic message span. Cool. So how do we actually report diagnostics? So we have a couple of places currently where we just throw an error. So one I can think of, also another thing I changed since last time is now the Lexa returns an optional token. If it hits the end of the source code, it just returns none rather than an EOF, so we can get rid of that. And then we have this error token, which so we do it here, and I think this is good because this basically doesn't halt the compilation. It tokenizes something, we don't know what it is, but we tokenize it into an error and then we move on. But that's not very useful when you're compiling something if it just puts an error token in. So why is this complaining? Yeah, because we no longer have EOF. And yeah, so like the parser just completely ignores any error tokens. So what happens, so let's go to, let's make a foo.do. So let's say we have 4, 5, and then we put a dollar or an and. This isn't a token that we currently support. So if I build, yep. And if I was to try to do this one, first of all, I think it might just hang. I think there's still some bugs in the Lexa. Yeah, it hangs. Ooh, I think I know why. Because... Yeah, we never advance the cursor for a error. So We do this, and then we say self cursor plus equal 1, return some error. Cool. So we do that. Now, it doesn't do anything because it just ignored this token. So if I just do print and run it again. Ooh. Interesting. Doesn't do anything. I would have expected this to just return an error token, and then in our parser... yes. So we parse until we hit a none. Because if we have a none, we were interpreting that as... because we had EOF there. Okay. So we don't yeah, because when the tokens returns none, we return none from the parser. So we actually never get past. So that's even worse. We never get past a token that we ignore. So let's report an error or a diagnostic. So the reason why I say diagnostic instead of an error is it might not be an error. You could have like warning diagnostics. So the diagnostic. We could also have the concept of a level, and you could have a warn and error, and then the diagnostic would have pub level, and you could have report error. There you go. And you could have report warning as well. So something like this. And then when you print this diagnostic, you can change the color, or if it's a warning, you can just continue compilation or interpretation. If it's an error, you can halt. But for now, I don't think we're going to worry about that. We're just going to keep it simple. Every diagnostic is an error, because I don't really know what we would have as a warning yet. I think a good warning would be stuff left over on the stack when you're done, because that could be an error, because a good program should have nothing left on the stack. If you have stuff on the stack, it means you've probably forgotten to handle something earlier. But anyway, we just want this to error. So if we go back to the Lexer, let's say that rather than an option of token, we return a... what would be the best way to do this? Let's do this for now. A result of an option of token or a diagnostic. Because then we get rid of this error token. We don't need that anymore. Because instead we return an error of a diagnostic. This isn't public. Report error. So, what would the message be? Probably we want to format unexpected character, and the span would be the, so we want to we want to advance the cursor afterwards. We don't want to return yet. We just want to say let diagnostic equal this, increment the cursor afterwards, then return error diagnostic. So the span would be, the offset is self cursor, and then the length is C len UTF-8. Okay, and then rather than returning none, we return OK none. A bit of a weird type to return, but Yeah. Otherwise, we could have a I've heard it referred to as like a diagnostic bag. So the Lexa would just have a vector of diagnostics, and then every time you encounter an error, you just add it to the diagnostics, and then you move on. Which actually, because then you can just like iterate them. Let's keep that in mind, but let's move on. So that return type has now changed, so our main no longer works. Yeah, so I'll let some token equal Lexa next. Let's instead I think it should be an option result. Maybe? Yep, there we go. Because this, yeah, this okay none. So it's none, this is some, error. Yeah, I'm kind of leaning more towards the diagnostic bag now, because I think having an option of result is a strange type to return. So yeah, while some result, we match the result. If it is OK token, we push the token. If it is an error of a diagnostic, well, now we can aprintln let's call it diagnostic, the diagnostic message. So now, if we try and do this, unexpected character ampersand, and as you can see, we ignore it and we move on. Now, is that a good idea? Because if you like, let's say you wanted to do this and you wanted to add them, but you missed and you typed this. What is that going to do? I didn't need to build. Yeah, that just says unexpected character and then it prints that. Maybe you want it to halt, maybe not. Maybe you want it to halt. So if there's any diagnostics in the Lexa, maybe you don't want to continue on to parsing. Yeah. So I think actually having the diagnostic bag makes sense. So let's have a vector of diagnostics. So what we do is we just initialize it as a new vec, and then instead of this wonky return type, it is just an option. Good. And yeah, maybe we still want the error token then. So if I return all of this back to how it was before I added that, and then we still want to return some token. So we still want this token. So let error equals this, self cursor plus equal 1. But we want to self diagnostics push a new diagnostic with, yeah, I probably should have kept this, but with format unexpected character. Maybe unexpected token? No, that would be more for like parsing, and then the span is, yeah, we do this after. This is a function, so we don't need to give it a name. Span, offset, self cursor len c ASCII len or UTF len. Yep, and then we want to some error or return some error. Okay, I think this is better. So now back here, we want to do this. So while some token equals Lexa next, if Lexa diagnostics, which is not public, it's a bit strange, but it'll work for now. So if diagnostics is there an is not empty? No. So it is empty if not Lexa diagnostics is empty. For diagnostic in Lexa diagnostics, eprint line diagnostic message. Return. Sure. Why not? So if you build that, yeah, unexpected character, close bracket. I think. Can I just do this? No. Whatever. Doesn't matter. I think also it would be nice if the character was quoted. Yeah. Let's also just do what is it? Cargo Clippy? Yeah, we have too many unused things. Let's not worry about it. So, yeah. We've just reported a diagnostic. But we still don't know where it was reported. Because when we do this, we're just printing the message. So I think it would be nice to have a function which is display diagnostic, which takes itself. And I think just that for now. And then in future, we will take in the source code as well. So then it can slice out the line which caused the error. So we can just do that. So we can say error. This message at yeah, this isn't going to be very useful at the moment. So if we do self message, self span offset, self span length. So now these don't have to be public. So instead we just do diagnostic, display diagnostic. So if we do this, oh, that's Cargo Clippy. Yeah, here you go. Error, unexpected character, close bracket at 4.1. So if we go here, not that one, if we go into foo.do. So now you should be able to see, yeah, you can see down here, the line and column. So if we go to 5, which is offset 4, you can see that points at the token. So what we could do is, yeah, we could pass in the name of the file and we could build something that's clickable. So let's do that. So yeah, file line column, yeah, file name as a string. So we can say at this. So file name. And I'm aware this won't work for when there's more than one line. So what do I call it? input path. We probably actually don't want to own this. So we can just pass it in by reference. So build. Here you go. Resources foo.do for. Yeah, this isn't how you report it. It should be line column, not offset length. So yeah. Later on, we can think about how we actually convert the offset and the length to a line and a column. But for now, I don't really want to do that. I think this is a good system. So let's just say offset length. So for now, we're not getting confused. So if we run that, unexpected character at resources foo.do offset 4 length 1. Failed to parse input. Let's instead say failed to tokenize input. So now we can do the same for the parser. So how come? Yeah, that's fine. So we never actually get to the parser if we have any errors. So we don't even need to make this token anymore. And we can just return none. No, because that stops the compilation. Okay. We'll leave that as it is. So now in the parser, there's not really anything that can go wrong in the parser yet, because we're not parsing anything too complicated. So we'll come back to this when we start to do lists. So now if we go to the type checker, this is the point where we want to start, replacing these panics. But I don't really want to start editing this code until we have proper signatures. So I think what we're going to do is we're going to commit what we have so far. So go to the changes. Yeah, we want all of these. So actually, let me let's be tidy about this. What is the command? There's like one that's like clippy, but it's just like is it cargo FMT? Yeah, there we go. And then cargo clippy. So yeah, bool is never constructed, but we're going to get there. Span is never used in OP. It will be for type checking, so that's fine. Yeah, we don't use this anymore. We can get rid of that. And that's fine. Okay, I'm happy with that. So let's add all of these. I don't know why I didn't add all those. And it's going to be introduce diagnostics. So commit that. So, also I don't think I'm on a branch. Yeah, I'm on main. Doesn't matter. I'm the only person on this project, so that's a bit of a silly mistake. It's fine. So, let's introduce the idea of a signature. So, maybe we'll put this inside the type checker for now. So fun get signature, and this would take a OP, so or an op. And what does it return? It returns a pair of vectors of types. So yeah, like this. So the signature of any operation is defined by what it consumes from the stack and what it puts onto the stack afterwards. So if we match, and we don't even need it to be the full op, it can be the op kind. So if we just match, let's call it op kind so we're not confused. If we match the op kind, it's not really what I wanted. I wanted this. So, just thinking about the generic ones. We'll get to those in a second. Yeah. We might need like an any, but we also need to be able to type check generics to make sure that, you know, if we're doing a reduce, that the types in the accumulator match the types in the function and the list, but we'll get there when we get there. So push int will just return a vec, of int, wrong way around. So it's consumes nothing and puts an int onto the stack, plus consumes two integers. So type kind int and returns one int. And it's kind of the same for all of these. So let's see if Rust Rover can figure out that these are all the same. Nope. Okay, never mind. If I instead just do this on the modulo, get rid of these, and then just say or. There we go. Dupe. Maybe this should take a immutable reference to self. Because dupe then you can match self type stack. Is it top, last? There we go. Some type kind. This will return a vec, so it consumes type kind, and it returns two type kinds. And I think we should implement, or we should derive copy on these. Because, does that not work? Takes 0. Because it's this. Okay. And then does it still complain? Expected that, but found that. Can I do this? Nope. Can I do this? Yeah. So we just dereference it, which is just going to copy it, but it's fine. It's just an enum. So do I have a clone somewhere still? Yeah, so I can just get rid of that. Yeah. But we're going to replace that anyway. So dupe is just looking at what's on the top of the type stack, and then is saying, okay, I want one of those, and I'm going to put two of those on. But if there's nothing on the type stack, this is where we need to report an error, but it doesn't feel like the place to report an error. So I think we should have an any type for now. Which is going to completely shit up our interpreter. Because, yeah, we shouldn't have an any type. If anything, we should have a generic type. Very interesting. So let's say we just say we want an integer for now. To do. This is not correct, but will fail anyway in the type checker. really we should expect a generic. So we can come back to this and add generics later, but we don't really need them now. So swap. Swap is very similar. It expects two type kinds. Yeah, this then gets into the same problem. So you know what? Let's have an any type. Yeah. We're only going to do any for signatures. We're never going to have an any on the stack, because the type checker will resolve it. So we don't want self anymore. We just want to say yeah, no, that's really not because then now it doesn't specify that these are the same type. I guess the type checker will sort that out. So we'll do this for now. I am aware that this is probably completely wrong. Let's keep the namespace just because it's easier to see what's happening. Yeah. To do. Any is a hack. Should use generics. So then swap. Yeah, so this is what I mean. Like we lose kind of the like information about this. Like we don't know that this is like potentially an int and a bool, and then we'll have bool and int. So yeah, we can come back to this. So then print takes in an any and just returns this. And I think I want to just keep it consistent with the macro. Okay, so you can see this is a lot nicer than this spaghetti. So what do we want to do? Let's get rid of all this for now. So when we type check an op, what we want to do? We want to say let ins outs equal self get signature of the op, and that's already a reference. For op in ops. And we expect the kind. Cannot move. Yeah, we can just borrow it. It's fine. And then we just say for input in ins match input. If it is any, then we just match self type stack pop. Sum is okay. None. We want to report a diagnostic. So let's add the diagnostics bag to the type checker. And we say, okay, none, self diagnostics push diagnostic, and then some kind of format. Oh yeah, we need to actually say this is the message. Oh, we're doing this wrong. It's a diagnostic report error. There we go. That's why I was getting confused. Format, type stack. So we want to say expected any, but stack was empty. and then the span is in the OP span, but I can't get that. So I think I just have to clone it for now. Let's see, what is a span? It's just 2 integers. We should be able to copy it. So, all good. So that's this is to do remove any and use generics. So that's in the case of any. Otherwise, yeah, I think we need to add generics. Because otherwise, we don't need to match the input at all. Because it's the same. Yeah, we just match this. And then there we go. Rather than saying any, also we were formatting nothing, we say input. So then, yeah, if we have some type kind, we just say if type kind equals type kind any. Okay. Yeah, we want to add partial ec. Oh, not like that though. To a type kind. Again, because it's just enum. But this is still wrong. So continue. Otherwise, if type kind equals input is okay. So if it does not equal, then we do this. Implement does not implement display. Yeah, we can just debug it for now. We should probably have proper displaying of types. Okay. So the problem with this is we now pollute the type stack when we push. Because what we want to do is for output in outs, self type stack push output, and that's it. But you see, we're going to pollute the stack with these any's. So we're going to lose type information. So we need generics. So I'm going to go have a think on how we're going to do that, and then I'm going to come back. So, okay, I think I have an idea. So generic is just a type kind that is has an index. So I think the type checker needs to have a next generic index. I haven't seen if this will work yet. This is just an idea I had, and I wanted to implement it and go through the process of figuring it out on camera. So the next generic index starts at 0. So when we are, yeah, okay. So when we're duplicating, we want to declare a generic. So let generic index equal, and now we do need self, and we need it mutably as well. So self next generic index, self next generic index plus equal 1. Maybe we should put that into a function, but let's see. So we want a generic, and let's just call this index just so we can do this. And we want to do this. Okay, so now we're saying we want a generic type, but we want the same generic type. Okay, so swap swap is more interesting. Swap, we want A, and we want B. So I think I am actually going to put this into a function because we're going to do this a lot. So let's say fun create generic, and this just returns a U size. So we say, yep, that. Fantastic. So instead of this, we just say let index equal self create generic. So then here, let A equal self create generic, and then let B equal self create generic. Good. So let's actually have this as anonymous, just so that this is easier. So this just becomes this. Yeah. So swap takes a type kind of generic A and generic B. Okay, Copilot's picking up what I'm putting down. And then, yeah. This looks wrong, but I think this is correct. Because you've got to imagine these are being evaluated left to right. So you're popping A, you're popping B, and then you're pushing A and you're pushing B. So they have swapped places. So you've got to imagine this is the order you want to encounter them on the stack, and then this is the order you want to push them onto the stack. So this looks wrong, but this is correct. And then print is basically the same as dupe, except it doesn't put anything onto the stack afterwards. Okay. That's better. But how do we actually type check this? So, this is now mutable self, which I hope won't cause any problems, but it should be okay. So, we need to have some sort of map or something like that for generic erasure. So I can never remember how you do hash maps in Rust, because I feel like you kind of have to like well, it should be hashable because it's just an integer, but then if we're just using a hash map with an integer, like that's just an array. So let's do let mute generics equal a new vector. Maybe this should belong to the type checker. Maybe this should belong to the type checker. Well, it doesn't matter. Doesn't matter. Because we do want this to reset. No, we don't want this to reset every time we type check. Let's do it like this for now. We're not worried about the REPL yet. So, if we get a generic. So if let type kind generic index equal type kind, we want to erase the generic if it's not already erased. So match generics get index. If we have some type kind, we'll sort that out in a second, so it's already erased. If we have none, then we want to generics. Is there an insert? Yes, there is. So you want to insert at index type kind, like this. So we have an integer on the stack, and we have print. Print takes in a generic. So we look at the type stack, at the type checking, and we see we have some, we have an integer in our type kind. Okay, what type kind does this operation expect? Oh, it expects a generic. So let's have a look in our erased generics. We don't know what 0 is yet. So let's say that 0 is int. And so we insert generics type kind int. If we already have it, so let's say erased if erased does not equal type kind. Did I get rid of the partial ec? No, it's because one of these is a... Yeah, so we want to borrow type kind. So if it does not equal that, then we say we expected this, but got this. So we expected input, but we got erased. Okay. So then for something like, I don't know, reduce, if you've erased the first instance of the generic, you now match the concrete type. I think that will work. We're getting a little bit pointy, and we might want to factor out this to compare types, because you might want to be able to coerce types. I don't know. We don't want was empty. So expected this, but got this. Yeah, that's fine. Okay. So that's if it's a generic. Yeah, and so this diagnostic is wrong as well. So expected that, but we got that. Okay. So let's see. We match the top of the type stack. If we have something, we say, okay, this should be input. If the input is generic, then we match on the generics. If there is something that's already been erased, we make sure that the top matches the erased. Yep. Otherwise, we say we expected... that's not quite right. We expected erased, but we got type kind. Okay. Otherwise, if there is nothing in the erasures yet, then great. We then insert the type kind that is on the top of the stack. Good. Okay, that's if it's a generic. So can I replace this with a match? Yes. And so if that. Does that work? Okay. Yeah, that's good. And then we can just factor this out. So this is check, or I guess it's type equivalent, or expect type, I suppose. So this takes, what is it? So we've got two type kinds and an op. So this is actual, and this is expected. So if expected does not equal actual, cannot be done to type kind. Yeah, we don't need to do that. If expected does not equal actual, they say we expected, but we got actual. And so here we can do some more complicated things like coercion. So we don't need these anymore. So that makes that a bit nicer. Okay. And then otherwise, we just do expect type between expected is input and actual is type kind, and we can just take them as both references. So that's a lot of code that we've written and not tested. So let's build this, and yeah, we never construct bool, that's fine. Let's try to compile a OK program. So this uses a generic, which I think is going to be okay because it doesn't put anything back onto the stack. So we'll start with this. So if we run arithmetic, prints 9. Okay. Okay. Well, hang on. We don't print any diagnostics for the type checker. So we type check the ops. If the type checker diagnostics, which needs to be pub, yeah, it's kind of weird just having a public field in the middle of it. Maybe we should rethink that, but it's fine. For diagnostic in the type checker diagnostics, we say failed to type check input. So, should still work. Yep. But. Now, if I get rid of this 5, expected int, but stack was empty at offset 2 length 1, yeah, which is the plus. Cool. But if I swap them, that's going to trigger the generics, and it's going to try and erase them with integers, and then plus is going to expect integer. So if this has correctly erased the generics to integer, this is going to be happy. Fuck. Okay. I think I know why. Match input. Match generics, get index, sum erased, expect type kind. Yeah. Okay, that's wrong. So self type kind. This should be what's on top of the stack. So this is at offset 9. So if we go to arithmetic, I'm pretty sure that's this. Yeah, so that's at column 10. So we didn't erase the generics properly. Oh. Yeah. Okay. So match output. Type kind generic index. Go on, can you figure it out? No, okay. Match generics get index, sum erased. We push erased. Why doesn't it like that? Because you need to dereference it. Okay. None not covered. Yes. If there's none, we just push the output. We just push the output because something else might erase it later. And yeah, we leave the generic on the stack. So yeah, this error might look weird, but that should be fine. So if it's that, otherwise we just push the output. Okay. So I think, yeah, we were type checking the inputs correctly, we just weren't handling the outputs. And there we go. Prints 9. So swap erases the generics to integer, puts an integer and an integer onto the stack, so then plus is happy. Okay. That's actually not that bad. Yeah. So this should really be inside the type checker, because if we go back to the idea of having the REPL later, if you've done a line that introduces some generics and then erases them, and then you go to the next line and you do like plus, it needs to know the generics when you do the next one. So we should have generics, which is a vec of type kind. Yeah, it's more erasures. It's more like an erasure, because these are the concrete types. You shouldn't put generics in here. So then we say erasures is a new vec, and we get rid of generics, and then here we just say self erasures. Self erasures. Not happy. What isn't it like? Cannot borrow. Fuck. No. Yeah, because that borrows it mutably. And I don't want to... Why don't we just... Okay, I didn't know you could do that, but that doesn't help that. So let's just yoink those out. I wonder if this is still not going to work. Yeah, it's still not happy about it, because, yeah, we borrow it mutably. Rust, please. I am not doing anything that's going to cause any problems. I understand, but this is annoying. Because I don't want to do this. I don't want to do that. In fact, that doesn't even work. What if I have a fun get erasure, which takes self immutably and returns a option type of, yeah, borrowed type kind. And that just does this. Because now I'm not borrowing it immutably. Is it okay with that? Self get erasure. Ooh. Oh yeah, we don't want to do this. We want to take an index. I got pranked by Copilot. Nope, that doesn't work. Fuck. How do I get around this? Okay, so I don't really want to spend time solving this. It doesn't really matter for now, but just going to clone the erasures when we do the matching, which is not the best, because if you have a really big program, that could be a big array, but the chances of it being a problem now, not so much. So, okay. We have generics, which is one of the things we wanted so that we could do lists and things. So if we go back to our to-do, well, we have diagnostics. We kind of have diagnostics. We have better type checking. Let's start lists. So this is where parsing becomes more interesting. So if we go back to the Lexa, we need new... Actually, let's do a commit first of all. So yeah, all of these introduce generics. Commit. Okay, still on the main branch, by the way, because I don't give a fuck. So we want open square and close square, and this is just a simple case of oh, you're so close. You're so close. Open square, close square. And I think for now we're going to go the simple route. So let's go back to lists. So we're just going to compile this. So we're not going to have any commas, which means we can't have any expressions yet inside a list. So we can't have like 1, 2 plus 3, 4, 5 to have 4 elements of like 3, 3, 4, 5. No. The only thing you're allowed to have in an array or a list are push operations for now. But as you can see, our parser is now complaining. And that is because we need to handle these new tokens, these new token kinds. So actually we kind of want a new op, which is going to be push array, push list. And that's not going to take a vec of token, it's going to take a vec of OP. And we're just going to have to trust that these are push operations, but I think it's going to be fine. Yeah. So if we have token kind open square, we can just to do that. Because what's more interesting is if we have a closed square. Because this should be an error. This implies that you've just gone like this. Because I think the parsing of the list is going to handle consuming the closed square for you. So I think this should be a error, which means we need to add diagnostics to our parser. So let's do that. And these need to be pub again, diagnostics, and then go on. Yeah, there we go. And then in our main, we just do this song and dance. This is getting a little repetitive, but we can sort that out. We can just say failed to parse input. And so we can just say if this happens, we self diagnostics push diagnostic report error format, and we have to shout it because it's a macro. Unexpected token this. We actually don't need to format anything because there's no format, and this needs to be a big S string, and the span is the token span, and we've shown none. Do we need to clone? Yes. Why do we need to clone? Didn't I make this copyable? Why does it need to be cloned? Expected span, but found that. Okay. So we just need to do that. That's fine. That's fine. So we can just change all of these into these. And in fact, we could probably, yeah, we don't even need to do that anymore. So actually we can just change all of these to token.span because it's copyable. And that's nicer. Yeah, because span's just 2 integers, that's fine. So then this should happen. Okay, we've broken all of this. Because we need to say, oh, what's the signature of push array? And to that, oh sorry, to push list. And to that I say shut up. We'll get to it later. And then the interpreter push list, again, I say I don't care. Value to do. Okay. Still not happy. What is it not happy about? What are you not happy about? Cannot move. Okay, whatever. Okay, so now it compiles. Yep. So if we go back to lists do, and if I just say 1, 2, plus print close square, and I try to interpret this, unexpected token close square, failed to parse input. Fantastic. But if I have an actual list and I try and compile that, not yet implemented. Look at that. Okay. Oops. So, are we peaking or have we consumed? We've consumed. So we're already past the open square. So we want to say while let some token. Do we already have something called token? Yes. While let some next equals self tokens get self cursor. We'll keep the to do here just because then we don't get distracted by all the squigglies. So while let some next, we match next kind, token kind, close square, we break. We also probably want to consume the token, but that's fine. In fact, we can just do that here. No. No, yeah, that's fine. This is probably, we probably want to do a bit of recursion, but I think when we're just allowing push, I think that's fine. So we break token kind push int int literal value. So we want to have a, there we go, let new ops equal rec new. So we want to ops push op, and we're kind of duplicating the parsing of integers. So if I go up to here, yeah, span token span. Oops. We're duplicating this parsing. I don't mind that. Let's get this out of the way. So yeah, we push that. So once we have more push operations, this is going to get a bit more awful, but for now, that's fine. Otherwise, self-diagnostics, push, diagnostic, port error. So you just say only push operations allowed in lists to string next span. Okay, so that then does this. So now we've done this. So if it's none and we haven't broken, then that's another error. So actually we should say while this is more like while true. Bear with me. While true, let next, or match this. If it's sum next, then we do all of this. But if it's none, that's an error. And we just say ooh, what would be the span of this? Let's save. Oh, we can just use the. We can just use the. So we can say unclosed list, something like that, or list missing closing square, and then it will point to the opening bracket. Okay. So we have while true, and yeah, instead we should just say loop. So yeah, if we encounter that, and then also if we encounter none, we should break. Okay, so we have all our ops. So we just say sum op add missing field, op kind, push list, ops, span. Okay, here we go. Now we can do something a bit more interesting. So if we go back to Lexa, and let's impl span. So let's have fun from 2, and we can have start span and end span, and we say a span with an offset of start offset, but the length is the end length plus end offset minus start offset. So you go to the end offset minus the start offset. Is that right? Is that right? So start offset, we go to the end offset minus that. Yes. This gives us the length of everything up to the last token, or the last span, and then this just adds that length. So really it probably makes more sense to do end length. That's more understandable. So then the parser, the span is from 2, which we need to make pub. There we go. From 2, so start is the... Yeah, let's actually, instead of breaking here, we can return. Because here we have the span of next. So from token span to next span. Expected option op, but found that. Missing closing, yeah, so we just want to return none. Okay. Seems reasonable. Seems fine. Let's build that. Unused value, yeah, that's fine. Not yet implemented. Type checker. We have a list. We have a list. Okay. So this, I think, is going to be interesting. So we have a new type, which is list, which has a box of type kind. We can no longer copy. Yucky, stinky. So, yeah, we have to clone explicitly now. That's fine. That's fine. Icky, yucky, stinky. So, let's get rid of this bool. This bool is pissing me off. we'll get to bool in a minute. So, if we get the signature of a list, well, this has ops. This has ops. So, what's the best way of doing this? For now, let's just say let mute types equals this for op in ops. Let ins out equals the signature of that. Let's put a to do so that we can see what we're doing. And we want to say so ins has to be empty. So if ins is empty, so if it's not empty, self diagnostics push report error. This is I think I had it. This is kind of unreachable because the parser. So actually, let's just say it's unreachable for now. And if outs len does not equal 1, this is also unreachable. Okay. So this isn't right. We don't need a list of types. We just want let mute element type equal none. And let's help the compiler and say this is an option of type kind. And we say match element type. If it's some type kind, then we simply expect type. Which way around is it? It's expected. Oh, it's actual expected. So the actual is the op. The op is the op. Type kind is that. Outs get 0 unwrap. Yes. Value used after being moved. You need to be like that, I think. Yep. None. Then we simply just say that the element type is some this. So let's just say let out equal this. So, and that's a reference, so that's fine. And we say element type equals some out clone. Oops. Because we can no longer guarantee that it is copyable. Or it's no longer copyable. So we have this. So now we have the element type. So we have if let none equals element type. No. Match element type. So if the list is empty, then this is a generic list, because we don't know what's in it yet. We could add stuff to the list and then we erase the generic. But now it's empty. So this is match element type. So we return a vec of nothing to consume and a vec of type kind list box new. Why doesn't it like this? Expected option of type kind but found. Why do you expect an option? Whatever. I'll keep typing and see if it figures itself out. So we want to let generic index, or just let index equals self create generic. Oh, I know what I'm doing. Wrong. None. We do this. Wow, I've messed up. There we go. Index equals self create generic. And then this is box of new type kind generic index. Okay, and we don't need the return. Else, if we had some type kind, Do we already have a type kind defined? Nope. Otherwise, then this is simply a list of box new type kind. Okay. So this pushes a list onto the stack. So I think we should do something like import format display for type kind, just so we can see things a bit nicer. So if we match self, int is that list, we want the L type. So this I will say is that L type. There we go. And then it's recursive. And then generic. Let's have it like that. So now we can print type kinds nicer. So we can do this. Do I do any more? Yep, we do one here. That's it. So now we type check lists. So I can say 5 plus, and this should fail because we can't add integers to lists. Maybe we should. Maybe that's concatenate. Maybe that's a weird thing to do and it should be an error. Expected. Okay, that's the wrong way around. That is the wrong way around. So type checker. We are expecting. So actual. Yeah, this is the wrong way around. Is that the one that we were calling? Expected int, but got list of int. At resources list do offset 14. So if we go to list do, I'm pretty sure, yep, that's column 15, so that's offset 14. There we go. It would be nice if we also reported where the wrong type is, but we have all that information, so we could figure that out later. But for now, doesn't matter. So that's pretty cool. And I'm pretty sure we can do stuff like for that swap. So we have generics. So actually, yeah, if we do this, I think it will still be fine. Yeah. So now the swap has made this a generic. We resolve the generic to a list of int. Very cool. So now we need to interpret that. So if I say, okay, well, print the list, not implemented. Because, yeah, we aren't pushing a list. So we need a new kind of value. So we need a list, which is a vec of values. How about that? And here we go. Now we've completely messed up all of this, which I said last time. As soon as we add another type of value, this is going to fall to bits. And it has. So we need to import add for value. Do that. The output is value. Okay, so we want to match self RHS. Int that. Otherwise, what do we do? That's very funny. Why can't we do that? Because it's value. Yeah, okay. That's very funny. If it's not an int and an int, it just constructs a list. Yeah, we don't want to do that. That's not right. We just want to eprint line. We cannot add that and that self RHS. I expect a value. Okay. Well, we'll just say it's unreachable. Cool. So now we kind of want to do this for sub. and this is sub, and we want to do mul div div, go away, div, and is it called mod? Is it rem? And we implement rem for value. Okay, where's this to do come from? Go away. Okay. So now we just say let AB equal that, and then that push value A plus B. Okay, let's just paste all of those just because it's quicker, and then minus is minus, multiply is star, divide is div, and modulo is this. Okay, and then print, just do that, and then we should implement display for value. Why not? Seeing as we're going to be printing a list. So if we import display for value, we match self, our remaining patterns, list, value. We simply just print. What's the signature of this? Right F that value. List values. We have to, yes, but vec doesn't implement that. So it needs to be values, was it join with space. And join. Why doesn't it like that? Method join exists for struct, but its trait bounds were not satisfied. Value. Ooh, so we want to get to map the value to string first. No? Collect. Hang on. I'm too Java brained for this. So we want to collect it into a single string, joining by spaces. Is that like joining, or So what type does this return? Map. So Rust join map. Must map join string. Join iterator of str. That's what I want. Collect string. It's closed. Intersperse. Fold. Okay. Fold. What was the accumulator? String u. This feels. Do not check the allocated memory usage. It's probably not great. Why is it not like that? Expected str but found string. A plus B plus. No, we want A plus that plus B. Okay, whatever. Whatever. This is already getting quite long. And we haven't implemented push list. So what do we do? So this is actually ops. So we want a yeah, this is a bit wonky, but let's say let moot values equal vec new. Oh, come back. There. For op and ops, patch op kind, push int, not self stack, but the values push, otherwise unreachable, and we just say push list of values. Okay, this is going to get kind of wonky if we add more push, but I don't think we're going to have that many push operations, so I think it's fine. There's better ways of doing it. Ooh. Maybe it was right before that it should have been a plus b plus that. Yeah, I would prefer it if there wasn't one. I'd rather it was. What was the other one? Intersperse, or into iter into join. If I just collect into a vec of string and then say join by that. Why not? No rules expected this token. There we go. How about that? There we go. That's what I wanted. So we can print lists. How about that? And I can say 6, 7, 8, 9, 10. Swap, print. So that will swap them. It will print 1 to 5, and it will print 6 to 10. Just like that. Okay, I think we've accomplished quite a lot in this. So I think let's just run a cargo clippy. Oh no, a cargo FMT, and then a cargo clippy. Cool. Okay, we don't need to borrow that anymore, and we can just say first, which is still an option, so we still have to unwrap it. Thank you very much, Clippy. Very good stuff. So introduce lists and commit. So I think that's a good point to call it for this episode. I think I'm going to go take a break, and I'll come back later today and we can implement functions. But I think that's going to be a separate episode. But I'm going to upload all of these in one go so that, it's all there ready to watch from the get-go. So hopefully I'll see you in the next part, where we can actually start to do things like this. And then do starts to take shape. So yeah, I hope you've enjoyed. Thank you again for sticking around this long. I appreciate it. This is probably quite niche content, but I'm not really trying to make something that's like, mass appeal. I want to demystify making a compiler, playing around with this idea, and I would find this very interesting. So if I find it interesting, hopefully there's someone out there who also finds this interesting. But hey, so yeah, let me know in the comments what you like, what you didn't like. Subscribe, like, all that good algorithmic jazz, and I'll hopefully see you in the next one where we implement functions. So See you then. Bye.